Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to the final lecture in this NPTEL course on nonlinear control. So we were looking at sliding mode control, and we sort of looked at last time a way for chattering attenuation, right? And after that we started to discuss the notion of equivalent control, right? What is equivalent control? It is basically the control that you obtain from the fact that your sliding variable goes to 0 in spite of the disturbance beyond a certain time, right? So this is a very important and interesting idea, because this equivalent control is obviously not an implementable control, and this is the actual control. But the fact is, the actual control in a time average sense must go to the equivalent control, otherwise there's no way that the system would remain on the sliding surface, right? Therefore an estimate for the equivalent control is simply a low pass filtering of the signum function here, and that's what is implemented here. And essentially now what we can say is that from here you can see that if you simply match this guy with this guy, yeah, if you as you can imagine, this has to match, right? Otherwise there is no way, you understand, there is no way that ideal sliding happens, right? And therefore once you match these two, you understand that this quantity and this quantity have to be the same, right? So therefore what we are essentially claiming is that a very good estimate for f is rho low pass filter of signum of sigma, right? For t greater than equal to tr, right? And you understand this becomes a very nice way of estimating not just disturbance but any derivative for that matter, right? Because where was the disturbance? The disturbance was actually in x2 dot, right? So even if there was no notion of control, even if there was no notion of control, you could in fact compute the derivative using this idea. I mean, because of lack of time, we are not going to get into that, but this is very closely connected to the notion of a sliding mode differentiator. Yeah, it's a very nice way of obtaining a differential, or in fact obtaining any disturbance signal. Yeah, so what have we done? We've taken simply the signum of the this sliding mode variable, and we are scaling it by this rho this rho which is obviously greater than L and all of that, right? We've already designed that. And so we are simply scaling by rho this low pass filter version of signum of sigma, and we are saying that this is a great estimate for any disturbance, right? And that's great, yeah, because that is what we will sort of use in trying to look at the notion of a super twisting control. Yeah, because until now you have seen that the chattering is not still completely gone. Okay, so what is this super twisting control, right? So you see that even though the chattering was gone in the first level, in the second level, that is, even though the chattering was less because we use an integral control, for example in this chattering attenuation kind of idea, still there is going to be chattering, right, at the next level. So it's not like you're going to completely get rid of this. But super twisting controls are a sort of quite an amazing way of getting rather smooth controls, right, are a very good way of getting rather smooth controls. Okay, so let's sort of look at what is the super twisting control. So what's the idea here? I'm going to go back to the original treatment here. If you see, what did we do? We had this half sigma squared as our V, right? And then we constructed our control as minus rho signum sigma. Yeah, that, I mean, the V is already cancelled, the CX2 and all that, so we are not worried about that anymore. But we've constructed the V as minus rho signum sigma, right? So now we do something slightly different, right? And that's what is the title here. It's a super twisting control, and this is due to some really interesting results from Utkin, etc. Right? So what is the super twisting control? You remember that we had sigma as x2 plus cx1, and we had v as 1/2 sigma squared, right? And of course you had, you know, what was x1 and x2. So if you look at v dot, we had taken it is sigma sigma dot, which is x2 dot, which is u plus f plus cx2. I am deliberately not writing the arguments of f just to save some space, right? And what did we do? We said that we will prescribe u as minus cx2 plus a new control v, and so this becomes sigma times v plus f. And this is the point when we had prescribed v as minus rho signum of sigma, right? Now this is where we prescribe a different control, right? We say that our v is not going to be minus rho signum sigma, but it is going to be minus rho sigma to the power half signum sigma. Okay, all right, minus rho sigma to the power half signum sigma, right? Now let's consider for a moment, say there is no disturbance at all. Say f is in fact 0. Then what happens is that v dot becomes minus rho sigma to the power half times sigma signum sigma, which is basically, this is just absolute value of sigma, so this is just minus rho sigma to the power 3/2. Right? This is what you have. This is minus rho sigma to the power 3/2. Okay. Now, so let's see. So right. So I'm just trying to see how we can do this. So I want to write this in terms of the v itself, right? And so that's my primary question, right? So this is actually going to be if, yeah, so this is implies sigma is somehow equal to square root of twice v, is what I get from here. And if I substitute it here, right, the absolute value of sigma is square root of 2v. If I substitute it here, I will get minus rho 2 to the power half, so 2 to the power 3/4 times v to the power 3/4, right? Okay, great. So it doesn't matter what I choose my rho as. It's evident that this is less than 1, so implies have finite time convergence. Okay, have finite time convergence. So it's not like we've achieved anything new in terms of the convergence. The convergence is still finite time convergence for the variable sigma, the sliding variable sigma. However, something really cool has happened, right? My control has changed. Yeah, let's not worry about u, let's just look at v, because u is just a smooth term along with a v. Now earlier the control was minus rho signum of sigma. So what was the earlier control going to look like? If I try to plot it, let's see, let me take a different color. If right, the earlier control was depending on the sign of sigma, right? It was going to jump between the the earlier control would be something like this, right? Depending on the sign of sigma, it would look something like this, right? So this is the old control. Yeah, but the super twisting control is rather nice. It is not just signum of sigma, it is signum of sigma multiplied by the square root of sigma. And this makes it rather nice and continuous. Yeah, so this is rather cool. Yeah, why? The control is not going to be these jumps anymore at all, because even if sigma becomes, here what was happening was, even if sigma became slightly positive, you had this guy. If it became slightly negative, you had this guy. It's just moving from this to this, this to this, this to this. It was like a bang bang. Here the movement is much more smooth. If it's slightly positive, then you only have a slightly up curve, slightly negative, slightly up, and so on and so forth, right? So this you will have as the super twisting control. Now the only problem is when there is actually the disturbance, right? It is not really cancelling the disturbance term. If you notice, the whole purpose of rho signum sigma was it was dominating the disturbance term. This guy is not doing that. And so what do we propose? We propose that so if you look at what happens in the presence of disturbance, is that the sigma dot dynamics, right, starts to look like minus rho sigma to the power half signum sigma, because because the cx2 is already cancelled, the sigma dot will just be this plus the disturbance. Yeah, so you see the disturbance is not really compensated. Okay, not really compensated. So in the presence of disturbance, you will not get convergence to the sliding surface, right? So what do? We actually use the idea of this estimator, right? What is it? Of course we have this assumption that f dot is also less than equal to some L bar, right? And then we construct our V as minus rho signum sigma plus a variable W, where the W is now an estimator, right? Where the W is now an estimator of F, right? Okay, so W is somehow F hat. Why does this work? This is exactly from the notion of the equivalent control, exactly coming from the notion of the equivalent control, right? If you look at this, what is the equivalent control? We say that the estimate is simply a low pass filter, right? And what is the low pass filter? It's something like this, right? So here the only thing we've done is we've not put in a low pass filter type term. We've simply kept it at this B signum sigma, right? And this also works, right? So this is from the notion of equivalent control, yeah, you can actually estimate, right? You can actually estimate the quantity f. Okay, you can actually estimate the quantity f, and that's the whole sort of really cool idea. Okay, that's the whole interesting idea. That, of course, you can always have a, there's no problem if you have a minus kW as well, no problem, right? But this works, right? This will be an estimator of f, and that is essentially what you apply on top of your super twisting control, and this will also compensate for the f itself. Okay, this will also compensate for the f itself. Of course, we are not specifying what b is, so we'll just say b large enough. Yeah, because if you remember here also, this rho was large enough to compensate for f dot and so on and so forth. Okay, so again, we have shown these without proof, so obviously you cannot say that this is a complete rigorous treatment, but the idea is the control obtained from super twisting is going to be much nicer, much cleaner, right, than anything that you will get from the typical classical sliding mode control. Okay, the final sort of notion that I want to introduce is the notion of second order sliding mode, right, or higher order sliding mode. You can always have higher and higher order sliding mode, but I'm simply going to introduce motivate this using the notion of a second order sliding mode. All right, so what is the notion? Earlier we constructed sigma as x2 plus some cx1. Okay, and we said this is first order, yeah, because it essentially it is what does it do? It sigma goes to 0 finite time and slides on sigma equal to 0 for infinite time, right, until both states actually go to 0, right? You remember the picture was drawn probably in the first page itself here, first and second, right. You actually reach the sliding surface and then you keep sliding for infinite time until you reach here, right? So you are moving in a one-dimensional surface for infinite time, right? And this is why this is a first order sliding mode, right? And this what we say is when a behavior like this happens for a dynamical system, that it starts to move or restrict itself to a one-dimensional surface, then we say that there is partial dynamical collapse, right? Which means what? That you have started off with a second order system, two state variables, but you collapsed and started moving on a dimension 1 curve, right? That's a partial dynamic collapse. When you do second order sliding mode, you actually do complete dynamical collapse. So the target is complete dynamical collapse, which means what? Implies x1 and x2 both go to 0 in finite time. Okay, and how does one do that? One does that by choose non-linear sliding surface, right? What is this non-linear sliding surface? It's pretty straightforward, right? I choose my sigma exactly motivated by the super twisting sort of a expression. Instead of x2 plus c x1, I take as c absolute x1 to the power half signum x1, right? The purpose of having this super twisting type expression, right? I am going to use this, call this a super twisting type expression, because this is exactly what we used in super twisting control, right? The purpose of having this is to make sure that this is a nice continuous function, right? Otherwise, if I just use c signums x1, then it's not continuous, right? And that's you cannot even categorize that as a surface, right? So as I said, purpose is to ensure continuous sigma, right? Because if it is not continuous, then sigma equal to 0 is not a surface, right? So therefore the idea of sliding mode, sliding surface, sliding manifold is not possible, right? If this is not continuous, so it has to at least be continuous, and that is what this sort of a term does, right? Now what do we know about this guy, right? What do we know about this guy, right? If sigma goes to 0 in finite time, say, then what do I have? I have x1 dot equals minus c absolute x1 to the power half signum x1, right? All I've done is substitute for x2 as x1 dot, right? Now if I take v as half x1 squared, I know exactly that v dot is going to be minus, because we did this analysis right here, right? We did this analysis exactly for the similar case here, right? Instead of sigma, there will be just x1, right? So I'm going to get v dot as minus c x1 absolute value to the power 3 by 2, and that is just again just pulling it out from here, that is just going to be this guy, right? Minus 2 to the power 3/4 c v to the power 3/4, right? And therefore what you have implies x1 goes to 0 in finite time, right? Because obviously this is less than 1, right? So that's exactly the condition, right? That v dot has to be some negative constant multiplied by v to the power alpha, where alpha is less than 1. And that's exactly the finite time convergence condition. Therefore x1 goes to 0 in finite time, and x2 is simply x1 dot, and therefore x2 also goes to 0 in finite time, right? And so we have what we will have what we want, right? This is, what does it mean? We will have finite time collapse, right? You will have complete dynamical collapse, because in implies have complete dynamical collapse, right? Why? Because we ensure that both states go to 0 in finite time, yeah, and stay there, right? So it's not sliding on a one-dimensional surface, it goes to a 0-dimensional surface, which is origin, right? Goes to origin in finite time, and we are done, right? And we are done, right? So that's the very interesting notion. Now what is it that we need to remember? We need to, of course, find out what u to use for sigma going to 0 in finite time, right? That's an important question. What will be the control, right? Now if you see, if I try to use v equal to sigma square to arrive at a control, I'm going to get pretty complicated things, right? Because I have to take derivative of this guy and all that. I have to take derivative of this guy and all that, right? Because if I, so sigma dot complicated, not that it's not possible, but yeah, it's fairly complicated. It's fairly complicated, right? Because once in order to do sigma dot, I'll have to take derivative of this guy, right? So however, it is well understood that u equal to, again, minus rho signum sigma works for large sigma. Okay, but again with a lot of chattering, right? This control also will have a lot of chattering. Okay, so notice that this looks similar to before, but actually it's different because sigma itself is different, right? Okay, but again this control, like I said before, also has a decent bit of chattering, right? Even though you have sliding, your non-linear sliding surface, but the point is only the sliding surface is non-linear. The fact that if you go across it this way or that way, across even a non-linear sliding surface, your control is still jumping, right? Then the other option is, of course, you can or use super twisting. Yeah, so whatever be the order of the sliding mode, the sliding, you can always switch to a super twisting control, right? Because then you get rid of the chattering issue in a very nice and efficient way, right? Because this is definitely going to jump across the sliding surface, right? Even if the sliding surface is linear, non-linear, it doesn't matter. It's still going to jump, it is still going to move around it, and if it moves across it, the control is going to jump, and therefore there's going to be high frequency chatter. On the other hand, the super twisting control, because it's not going to be rho signum sigma, it is going to be something like minus rho sigma to the power half signum sigma. Yeah, you are going to have a much more smoother performance. Okay, and that's sort of what you're looking for. All right. So that's sort of all we wanted to discuss in sliding mode control. We did first order sliding mode, we did second order sliding mode. We sort of understood how, using the notion of equivalent control, you can actually obtain the value of the disturbance itself. We understood the limitations in the sense that there is a lot of boundedness, uniform boundedness assumptions. We understood that there is chattering issues that we need to resolve. Super twisting control is one of the really cool developments in sliding mode control area, which actually gets rid of chattering very efficiently, right? And this can be combined with the function, the disturbance determination scheme, to actually get to the sliding surface. Yeah, so of course we did most of this without proof and with a very nice double integrator example. Things are significantly more complicated if you do more elaborate things for more general systems. And of course there is enough literature and books and texts in this area. So I have particularly been referring to the book by Yuri Stessel and others. Yeah, on sliding mode control. Yeah, there is quite a few authors. All the most of the pretty heavy lifters in the area are sort of co-authors in this book, and so it's one of the better written books. Most of the material that we've covered is from the first chapter. Yeah, and so as you can imagine, this is what we've covered is literally just the first chapter, in introduction to sliding mode, and there is so much more than this in sliding mode control, yeah, that we have not actually covered here. So that brings us to the end of this NPTEL course. I really hope that you enjoy learning through this course. and I also really hope that some of what you learned ends up being useful for you in the real world. And I would be very happy to hear here and on YouTube. Please tag me, please tag the course on your social network pages, and so that more and more people can actually take the course, learn from the course, and there is more interest in the topic in general. Yeah. So that's all from me. Thank you so much again.